Hello students, we have seen the concept of entropy and the principle of increase of entropy in our last lecture. In this video, we are going to study about the second law of thermodynamics in terms of entropy, TS diagram, and work done with the help of TS diagram. So let's start. Let us see first the second law of thermodynamics in terms of entropy. In terms of entropy, the second law of thermodynamics can be stated as that every physical or chemical process in nature takes place in such a manner that the total entropy increases. This is nothing but the principle of increase of entropy that we have seen in our last lecture. So, what is the second law of thermodynamics? Every physical or chemical process in nature takes place in such a manner that the total entropy increases. Now, in order to put this law in mathematical form, let us take S1 and S2 to be the entropies of a substance in the initial and final states. So, what we are considering, we are taking S1 and S2 as the entropies of the substance in the initial and the final states, and starting with the arbitrary 0. Then we can write the change in entropy as S1 minus S2, which is equal to integration from the limits a to b dq by t. Or simply we can write this as equal to S1 minus S2 is nothing but ds, and therefore we can write this as dq is equal to t into ds. So what we have done here is, instead of this S1 minus S2, we are writing this as ds, and this is equal to, if you write in the simple form, it will be dq upon t, and therefore we can mention dq as equal to t into ds. This is nothing but the second law of thermodynamics in the mathematical form. So this is called as the mathematical form of the second law of thermodynamics. So what is a TS diagram? Now earlier we have seen PV diagram, the pressure volume diagram, which is used to explain any of the thermodynamic process, and this curve is the curve given by Carnot cycle. Now in this case, we know that the substance is taken from the state A to the state B, then C, then D, and back to the state A through 4 different stages. Now this thermodynamic diagram can be converted into a TS diagram. The temperature versus entropy diagram is used in thermodynamics to visualize changes to temperature and entropy during a thermodynamic process or cycle. It is a very useful and common tool because it helps to see the heat transfer during a process. So how do we draw this TS diagram? Now to draw this TS diagram, we will plot the entropy along this horizontal axis and the temperature along the vertical axis. Such a diagram is called as the temperature entropy diagram or the TS diagram. Now here we have the Carnot's reversible cycle shown in the PV diagram. Here we have AB and CD at temperatures, this AB and this CD at temperatures T1 and T2. So these are the constant temperatures. Now on the TS diagram, the isothermal curves are shown by straight lines AB and CD parallel to the S-axis. So this is the S-axis, and these isothermal curves are shown by the straight lines. Then here we have the curves B.Sc and dA, which are the adiabatic curves. Now these adiabatic curves are shown by the straight lines BC and DA, which are parallel to the T-axis. Now this resulting TS diagram is a rectangle ABCD. So with the help of this rectangle, it can be very easily found out the area under the curve ABCD, which represents the work done during the cycle. So now we are going to find the area of TS diagram, which will give us the work done in reversible Carnot cycle. Now for that we will consider Carnot's reversible cycle on the TS diagram as shown in this figure here. So this is the Carnot's reversible cycle, which is shown in the TS diagram. Now suppose that S1 is the entropy of the working substance in the state A. S2 is this entropy of the working substance in the state B. So here we have S1 and this is S2. So we are having the Carnot cycle, and S1 and S2 are taken as the entropies in the state A and B. Now Q1 is the heat absorbed along AB. We have seen that during this change there will be heat absorbed, and let us take this heat absorbed as Q1, which is the heat absorbed during the isothermal expansion at constant temperature T1, and Q2 is the amount of heat which is given or rejected in the isothermal compression at temperature T2 along CD. Now if you go from this A to B along this isothermal expansion AB, then the gain in entropy of the working substance. So we are going to find out the gain in entropy of the working substance while going from A to B. So this is isothermal expansion AB, and during this isothermal expansion AB, the gain in entropy of the working substance, it will be given by S2 minus S1, which is equal to Q1 upon T1. So heat absorbed here is Q1 at constant temperature T1. So the gain in entropy will be S2 minus S1 is equal to Q1 upon T1. Now when you go from B to C along this adiabatic expansion BC, there is no change in entropy. As you can see, there is no change in entropy, there is constant entropy. Now when you go from C to D, during the isothermal compression CD, there is loss in entropy of the working substance. So along this BC there is no change in entropy, and isothermal compression there is loss of entropy of the working substance, and it is given by S2 minus S1 is equal to Q2 upon T2, because Q2 is the amount of heat rejected and T2 is the constant temperature. And along this dA, there is no change in entropy because the entropy is constant. For adiabatic change, the change in entropy will be 0. And therefore, we can write from this equations 1 and 2 that Q1 is equal to T1, it is bracket should be here, so it is T1 into S2 minus S1, and Q2 is equal to T2 into S2 minus S1. So from the first equation, during this isothermal change, we have the expression Q1 by T1 is equal to S2 minus S1, where we can write Q1 is equal to T1 into S2 minus S1. And during this isothermal compression, we were having the expression Q2 upon T2 is equal to S2 minus S1, and we wrote this as Q2 is equal to T2 into S2 minus S1. And now we can subtract these two. So we can write this as Q1 minus Q2 is equal to T1 minus T2 into S2 minus S1. So from this we can find Q1 minus Q2 is equal to T1 minus T2 into S2 minus S1. Now what does this quantity Q1 minus Q2 represent? You know that the quantity Q1 minus Q2, it gives us the external work done in the cycle. So this quantity Q1 minus Q2 gives us the external work done in the cycle. And on the right hand side, we have the term T1 minus T2 and S2 minus S1. As you can see here, this T1 minus T2 gives you the length of this rectangle, and S2 minus S1 gives us the breadth of this rectangle. The length multiplied by breadth gives you the area of the rectangle. So therefore on the right hand side here we have the area of the rectangle, and on the left hand side we have the work done in the cycle. So what can we conclude from this is the area of the rectangle on the TS diagram gives us the external work done in the Carnot cycle. So this is our conclusion here. The area of the rectangle on the Carnot this TS diagram, it gives us, or it represents, the external work done in the reversible cycle. Now we can also find the efficiency of the Carnot's engine, and using this TS diagram we can write. Now we know that the definition for efficiency of the engine is that external work done in one cycle divided by the heat absorbed from the source. And just now we have seen what is external work done in one cycle. It is Q1 minus Q2, and divided by the heat absorbed from the source is Q1. So therefore instead of this Q1 minus Q2 we'll write T1 minus T2 into S2 minus S1 divided by, and from the equation 1 we are writing this as T1 into S2 minus S1. This gets cancelled here, and therefore we can write this as T1 minus T2 upon T1, and we can also express it as 1 minus T2 by T1. Thus the efficiency can also be found out from this TS diagram. So that is how we are able to find the this work done from the TS diagram. What is the importance of this TS diagram? Now this TS diagram is also known as taphogram. Taphogram is used in meteorology to give the interpretation of the temperature and humidity structure. The taphogram is also commonly used in weather analysis and forecasting. Also this helps us to find the work done per cycle, because the TS diagram is a rectangle, so it can easily calculate the work done per cycle. Therefore it is used by auto engineers to study the working efficiency of the engines. Also while studying they theoretically can calculate, as well as they can actually find the efficiency of the actual engine. So these are the importance of the TS diagram.